Welcome to Fast Math Solutions on Maths with EJD. In this video, we are talking about generating functions, and in particular, we are finding partitions of 5 into distinct parts using generating functions. So the goal is to solve the problem of finding the number of ways to partition n equals 5 into distinct parts using generating functions. So to do this, the first thing we will have to do is to define the step one. So we'll talk about generating function for partitions into distinct parts. Okay. Now the generating function for partitions into distinct parts is given by this expression: g of x equals all the product from k equals 1 to infinity of 1 plus x raised to power k. So I think we talked about this when we're talking about generating functions in combinatorics. So this is the expression for that. Now, this actually represents the sum of all partitions, into distinct integers, So that's the first step. Now, the second step, step two, we truncate. So truncate the generating function. Truncate the generating function for n equals 5. That's the second step we take in this situation. And here, say that for n equals 5, we only consider where k is less than or equal to 5, since partitions of 5 cannot include parts larger than 5, for sure, larger than 5. Thus, the truncated generating function is g of x equals 1 plus x raised to power 1 into 1 plus x raised to power 2 into 1 plus x raised to power 3 into 1 plus x raised to power 4, 1 plus x raised to power 4 into 1 plus x raised to power 5. That's how far we can go, because we are talking about n equals 5. So we can't go above this. And we know that the worst case there is that imagine if this one even stands out. So you have 1 times x raised to power 5. So you can have that. But of course, that it's not like that's exactly what we're going to have, but at least we stop we go as far as x raised to power 5. You know, this symbol means you're multiplying starting from k equals 1. So 1 plus x raised to power 1 plus 1 plus x raised to power 2 plus 1 plus x raised to power 3. And you do that till you get to infinity like that. So having done this step 2, now we go to step 3 where we expand. Step 3, expand the generating function. Expand the generating function. So in expanding the generating function, so now we expand the product to find the coefficient of x raised to power 5. So x raised to power 5 is the highest power we are looking for. So, and which corresponds to the number of partitions of 5 into distinct parts. For instance, here now we have g of x now equals, I mean, from all of this, we have 1 plus x into 1 plus x squared into 1 plus x cubed plus 1 plus into 1 plus x raised to power 4 into 1 plus x raised to power 5. So here we want to expand and make sure we do not get any power above x raised to power 5. So again, so we have 1 plus x into 1 plus x squared into 1 plus x. Okay, yeah, I think to drive the point home, right? We already said it, that this is all the products from k equals 1. In this case to 5, because we already know that that is 1 plus x raised to power k, right? And that means that when k is 1, we have 1 plus x raised to power 1. When k is 2, we have 1 plus x raised to power 2. When k is 3, we have 1 plus x raised to power 3. When k is 4, we have 1 plus x raised to power 4. When k is 5, we have 1 plus x raised to power 5. And that goes. So now we want to expand term by term to be sure we do not have any power above 5. So we can take them in pairs. First, we have 1 plus x into 1 plus x squared. So we can, when we take this, right, we have something like 1 plus x squared plus x cubed. That's what that turns out to be, because we can have 1 times 1, that's 1. Then we have x times x squared, that's x cubed. Then we have x times 1 in between, and then 1 times x squared. That's how that works. So we have that. So the next thing we're going to do is to now we now multiply what we have now by 1 plus x raised to power 4. So we can go for that. Now we have 1 plus x into 1 plus x squared into 1 plus x cubed. Sorry, 1 plus x cubed. That's the next thing we have. So if you multiply this by 1 plus x cubed, so we have, I mean, we already have this part, right? So this part is that part. And then if we do that, we end up having 1 plus x squared plus x cubed plus sorry, that's 1 plus x squared plus 2x cubed plus x raised to power 4 plus x raised to power 5 plus x raised to power 6. We have that. Then we go ahead again and multiply by 1 plus x raised to power 4. So we keep increasing it term by term like that. Now we have 1 plus x into, now I'm not expanding everything step by step because I mean, I know that's something that can easily be done. So 1 plus x raised to power 4 now. So if we do this, that gives us so for 1 plus x raised to power 3, that goes as far as x raised to power 6, because of course, we are multiplying these two together. So you can have 1 times 1, 1, x cubed times x cubed, that's x raised to power 6. Then every other thing in between can follow. In this case now, if by the time we include 1 plus x raised to power 4, I'll just write what we end up having. If you do all of that. So already, the whole of this is the same thing as what we have here. All right. So we are multiplying this whole thing by 1 plus x raised to power 4. So, the smallest number is going to be 1, and the highest one is going to be x raised to power 10, because x raised to power 6 is going to multiply x raised to power 4 here. So the result in that case is 1 plus x squared plus 2x cubed plus 2x raised to power 4 plus 2x raised to power 5 plus 2x raised to power 6 plus 2x raised to power 7, then plus x raised to power 8, x raised to power 9, and x raised to power 10. X raised to power 10. Okay. Now, having done that, we also go ahead and multiply by 1 plus x raised to power 5, which is the final part of this. So we have 1 plus x into 1 plus x squared into 1 plus x cubed into 1 plus x raised to power 4 into 1 plus x raised to power 5. And of course, you already know that from here to here, that is from here to here, right? We already have it in this whole place. So, the highest power you're going to have here is x raised to power 15, while 1 is the beginning. So, in this case now, so we have all of what we have here times this. But then we can already see that we need only terms up to x raised to power 5 because that is our area of interest. So we now see that we only need we only need terms up to x raised to power 5. So normally we didn't even have to go all that way. I guess we should have stopped. Okay, terms in x raised to power 5 for every possible thing we have here. So we only need terms up to x raised to power 5. So focusing on this, we collect all those terms. We collect where x raised to power 5 appears. So it will appear from, these are the possibilities now. We have 1 times x raised to power 5. We have that. We have x times x raised to power 4. We have x squared times x cubed. These are the only possible places where x raised to power 5 appears and no more. Okay, these are the only 3 places where we can have power x raised to power 5 maximum. So in that case now, each term contributes one partition. Okay, so we now have that coefficients of x raised to power 5 will now be 1 plus 1 plus 1, and that is 3. So that takes us to step 4, where we interpret the result. So step 4, interpret the result. Okay, so we can now say that the number of partitions of n equals 5 into distinct parts is 3, corresponding to the following partitions, So the first one is where you have 5 directly. The second one is where you have 4 plus 1, based on what we have up here. So you have power 5, then you have 4 plus 1, talking about the powers. And then the last one is where you have 3 plus 2. Okay, so we can now conclude that the number of partitions, the number of partitions or rather the number of ways to partition n equals 5 into distinct parts, is 3.